everybody, and welcome to this new episode of My Data Guest. Today, I'll be the host of the episode, and we have with us our second host, who is going to be our guest this time, Rosaria. How are you, Rosaria?
Hi, host.
All right. Today, the episode is all about LLMs. We're going to talk about large language models, and in particular, this will be a very, we can say, technical episode, but Rosaria will try to make this, all the concepts that we're going to see, very simple, hopefully also simple for me, and I will try to catch up and try to understand finally what an LLM is about. And we start with something very simple, which is a question that I get often. And the question is, why now? It's been a while LLMs are around, and in general, all the technologies and the concepts behind LLMs.
Thank you. Yeah, that's a question I get often too. So I've been working in the past with recurrent neural networks and long short-term memories, still for prediction of next word in language processing, in natural language processing, but we never got the results that the large language models are getting now. So often I get this question. So what is it? Is it just a large neural network? Which of course it is. It is a large neural network. It is very large. But is that all? Is that the whole explanation of why the large language models are working so much better than what we used to do? So I was also a bit puzzled. So I started studying, and I think I discovered the secret sauce of the large language model. So is it true? It's true that those are large. They are trained on huge amount of data. They have a huge amount of parameters. They are based on a hardware that we couldn't do on our own laptop, like even 6 years ago. So it's not something that you can do on your laptop in your kitchen anymore. So this is all true. But at the same time, they also have a few tricks, a few things, a few innovations that made the whole prediction, the whole generation of language and understanding of language possible. At least much smoother than what we were able to do with the recurrent neural networks. And I don't know, so the recurrent neural networks, it's not just a feed-forward neural network. You have this auto connection that allow you to go back to the same layer with the current information so that you can have, a cyclic forward of the information, iteration after iteration. So they gave up on that. There is no recurrency anymore. It's really only a feed-forward neural network. So the recurrent neural network at that time, we needed them because, you have a sentence, you have many words, and let's say the cat is sleeping on the sofa. It's important to know who's sleeping and where is sleeping, whoever is doing the action of sleeping. And so you need the context information. With the recurrent neural network, the context information was all summarized in a status variable, in a status vector, and this only one vector was responsible for summarizing the whole context information. So in the large language models, they have removed that. So there is no more auto connection, there is no more status information, and they have expanded this context information by using all the context and just weighting which part of the context is the most relevant for our task using a weight matrix. So that's all they have done. All. And that's what I think the big change with respect to the recurrent neural network. So now you have available the whole context. Of course, it's much more computational intensive, and you can weigh which context, which part of the context is relevant and which not, thanks to the attention mechanism. Another thing that I think is, made the whole large language model successful is the embedding. This has been around also a bit for a long time, but it allows you to semantically group words, tokens, making the whole search for words and for meanings much faster than just associating input to output like in a normal neural network. So there are a few things that they have introduced. Of course, the size too, but there are also these two tricks. The attention mechanism inserted inside the transformer block and the embedding. Absolutely.
Yeah, that's interesting. I remember when I was deeply involved in a project where I had to use LSTM, and that helped me a lot to understand the context of the time series that I was working with, because it was a very long time series and I had many time series stacked on top of each other. And with LSTM, I had this memory that was helping me to answer questions based on the past. But then, as you said, of course, this attention is all you need, the famous paper from Google, changed the game.
That's the paper that introduced the transformer.
Yeah.
But the attention mechanism, I think it was before. So I did a bit of a research. So I think it came, it became popular after the Google paper, The Attention is All You Need. But I think it was an idea that came out before. Then they put it all together in this transformer, and then the transformer concept, of course, including the attention mechanism, became very popular. Yeah.
Funny fact, yesterday I told a friend of mine that I was about to record this episode. And I said, tomorrow's episode is going to be cool. And he's a software engineer, so he's not working with AI solutions, AI tools. And I said, and he was like, okay, well, what are you going to do? And I said, it will be about Transformers. And he was like, okay, like the ones from the movies.
I don't, they always ask that, but I haven't seen the movie.
But yeah, that's what he asked me. And and then we were laughing a lot about that. And I said, I'm gonna say that tomorrow in the podcast recording, but I don't wanna share his name. Otherwise, he's gonna lose his job. Anyhow, I don't want to share anything about him. All right, you said something about more data, and more data is part of my life now, because as a data scientist, I've been told many times, I've been asked many times, why do you need more data? Why do you need more data? And it's always complicated to answer this question. So what is more data, and how large is a large data set? What kind of magnitude of data sets are we talking about?
So the part that I have explored is the GPT part. So the GPT-4, at least as far as I know, the details of the training and also of the data that have been used for training, they haven't been released. So I don't know what they're using, but for sure it's more than what they used to do for the GPT-3. The GPT-3 was not working as well as the GPT-4. So for the GPT, they had around 500 millions of tokens, so billions. They had around 500 billions of tokens. They said they used only 300 billions. I don't know why they didn't write why. And most of that, they came from web crawl data from the common crawl data set and the web text 2 data set. The web text 2 data set came from the Reddit posts. So those were Reddit posts, I think between 2015, something like that, which I have to say, it amazes me because I was on Reddit at that time, and it was horrible. It was really, really not a nice place to be in. So I'm surprised. Exactly. I'm surprised that ChatGPT turned out to be so polite, but okay. And then they had a bunch of books. So they had a internet-based book corpus. I think they took all possible books, digitized them, or took them already in digital forms, and then fed them into the GPT. So the GPT-3, and that was still a small large language model, used 500 billions tokens. So those are considerable amount. Now it must be more, for sure. We are going into the direction of the trillions. The same with the parameters, right? GPT-3 also had something like 175 billions of parameters, and now we are going for sure in the trillion kind of range. So yeah, they are large. They are definitely large. As I said, it's not something that you can do on your laptop in your kitchen table anymore. You need a center. You need a data center. You need a bunch of parallel computers. You need some more engineering organized lab to run this kind of trainings.
Yeah. And speaking of parameters, we're talking about huge LLMs, but at the same time, I'm also running small LLMs on my Raspberry, and people are always they're kind of amazed about this topic of running an LLM on your machine. But you can actually do it, because there are a lot of LLMs that are like small, very specialized. So it's true that when we talk about LLMs and GPTs, we talk about huge models like this kind of generalized models that are going in the direction of being an AGI maybe one day. But these kind of models, But at the same time, there are also a lot of small models that you can use. And for instance, I'm running some small models on my Raspberry that I use for small tasks, and they're usually really good, even though they're small. And of course, you see the limitations when you try to ask complex questions. And sometimes they hallucinate, especially when they have to, I don't know, like speak
They go out
Italian or
of their
something.
comfort zone.
Yeah, they definitely go out. They definitely go out and they
Yeah, but they're
they
coming back.
hallucinate.
The small language models, they're coming back because for some things you don't need the whole, all the
Yeah,
books of
exactly.
Shakespeare. You
Yeah,
just need your specific knowledge. Yeah.
yeah. Maybe I will start writing posts, LinkedIn posts for the My Data, I guess, with small models. Let's see what we get.
We can feed them with our lessons, and then you have a very
Yeah.
well trained
Yeah,
small
yeah, right. We
language
can do
model.
some fine tuning. All right. Speaking of training, because you said that this is not something we can train on our own anymore. And I can also add something to this question, like just this is a small comment. What I usually do with in terms of training LLMs is more like fine-tuning LLMs. So adding one layer at the end of this neural network, and in that layer, I'm adding more information. Maybe I'm trying to change the tone of the LLM with, I don't know, information that are coming from a chat where I have a lot of messages and I want the LLM to talk like me. But I'm not training the full LLM because it's too complex.
Of course.
But can you help us to understand what is complex, how much it costs? Do you have information about it?
So, what is reported, all these things, that the information from how they develop these models, of course, comes in bits and pieces. As I said already, the GPT-3 was 175 billions parameters, so considerable, not yet on the trillions, but considerable. So now probably we are in the trillion range. And I think I read somewhere that it costed 4.6 millions dollars to train. So this is not something I could do with my budget. You need a more organized entrepreneurship kind of initiative to train this kind of models. What you can do, you can take the generalist model exactly and then apply the fine tuning to make it good for your own specific task. Yeah. So those are the kind of numbers. And this one was the GPT-3, the one that was not working fantastically. So now with the GPT-4 and now the GPT-5 or even the Llama, I don't know how much they spend, but for sure it's not something in the budget of a single person.
Yeah, yeah. We also maybe I can add something about the parameters because I got this question many times when I talk about parameters and when I talk about the magnitude of the information that you have in a trained LLM. So usually what happens with LLMs is that if you write something like I like, then the possible output can be pizza, dogs, cars. And the idea is that you have a probability attached to each, you have a number attached to each, to pizza, dogs, and cars that are coming from these parameters that you have in the LLM. So the weights that the LLM learned during the training. And of course, if you have 1 billion of parameters, you can store more patterns. So you can have also style, facts, grammar, so not just the simple word that comes after I like, but you can have more information about what comes next. And that's why when we say that big LLMs with billion of parameters are really smart.
Yeah, but you can see, if I show you the architecture of the LLM, you can see quickly how, the beauty of the neural networks is that you can grow them as much as you want. It's not enough. You put 3 more neurons, 5 more neurons, 10 more neurons. So it grows very, very quickly. And they added these different layers. All these layers are layers of neural networks. So it explodes very, very, very quickly.
Yeah, that's cool.
I have a little slide to show you how the LLMs learn. So if you want, I can make it maybe more clear for. Okay, so the large language models, they are trained to predict the next token. Now, token, if you are not familiar with the tokenization process, since they use a subword-based tokenization process, let's suppose at least for now, that one token is one word. So the large language models, they are trained to predict the next word from a sequence of past words. So in this case, I have the cat is sleeping on the. So what could be the next word? The next word could be sky, that's an option. Another option would be a cactus. Another option, a shelf or a sofa. And then, of course, take all these possible solutions, all these possible next word, they come with a kind of a probability attached. And the sky, obviously, sounds unlikely. So the probability that is attached to sky is 0. On the cactus is technically possible, but maybe not so comfortable. So even here we are dealing with a low probability. And then with the shelf, it becomes more increasingly possible. And then the sofa is probably the most likely of the words to follow. So this is how they work. I just wanted to explain how the large language models are trained. At the end, it's just an auto-completion kind of task. You have a sequence of words, and the LLM is supposed to complete it with the most likely following word.
Yeah. And that's why people make fun of the LLMs and say it's just an auto-completion, because it is.
Considering how simple it is, it's an autoregressive model at the end. Considering how simple it is, it's actually performing pretty well. It's surprising how well it's performing, considering exactly that it was trained on such a simple task.
Yeah, makes sense. And what about the attention mechanism? You said that is the base of transformers in large language models. What kind of role does it play?
Okay, so that's what I prepared for today. This is the architecture of the large language models. You start with a tokenized text. The tokenized text goes through the embedding layer. So now you have a sentence. Each word, as I said, let's take word equal token, even though it's not completely correct, but it's easier to understand. So each word becomes a token, and then each token receives an identification number. Each identification number goes through an embedding layer, and it's associated to an embedding vector. So each word becomes a vector of numbers. So this is the embedding layer. We can talk about the embedding process in another episode. After that, the embedding vector, so each vector of numbers representing a word, so a sequence of embedding vector goes through the transformer block. And that's the part that represents the big innovation. The transformer blocks that contains the attention mechanism, and that's the big innovation of the large language model. Just to tell you about the size of these models, the transformer blocks, I think GPT-3 had 96 and GPT-2 had 48. So GPT-4 hasn't been released how many they have, but you can see how complex the architecture is, because one transformer is already complex. You have to repeat it 96 times, combine the results, it becomes quickly something very complex to handle.
Yes.
So the transformer blocks, this is a bit of a schema. So that there are a bunch of normalizer and dropout layer in the middle. They are sprinkled a bit everywhere because the normalizer, as Alessandro said before, it's introduced often so that the numbers that you get can be interpreted as probabilities. They are not probabilities, they are some kind of scores, but since they all sum up to 1, somehow you can interpret them a bit as probability. And the dropout layer, they're also sprinkled a bit everywhere in this architecture because they introduce some randomness in the training of the models and allow the weight to, let's say, the neurons to become more productive by introducing random inactive neurons. Anyway, so besides those, then there are 2 components only inside the transformer. One is the attention mechanism, so the masked multi-head attention, and the other one is just a feed-forward neural network. The feed-forward neural network is a classic one. You get an input, you produce an output. The output, in this case, is a list of possible next tokens. Each of this token with some kind of a probability attached. So the masked attention mechanism is the new thing. So let me see. I'm going to skip this one. Okay. So let me see how the attention mechanism works. So you start from a sequence of embedding vectors, right? Here I have the fox jumped over the lazy dog. So each word becomes an embedding vector. So you have a sequence of embedding vectors. One word, one embedding vector. So what you want to make it a bit more complex. So you move from the embedding space to a bunch of different spaces, 3 different spaces. The first space is the space of the queries. So those are the words and the words that you are currently focusing on. Then you want to project all your words into the space of the keys. This space contains all the words that are in the context and that are part of the whole sentence, right? So now let's remain with these 2 new spaces. In the queries, I have a number of words and I'm going to focus on one. And in the keys, I have all the words from the sentence. So what I want to know, for example, if the sentence is the fox jumped over the lazy dog and the word I'm focusing on is jumped, so the query at this moment is jumped, I want to know how important is with respect to jumped, to understand the meaning of the sentence. How important is fox? How important is jumped? How important are all the words in the sentence? So if I am able to quantify the importance of each word in the sentence, of each key with respect to the query, then I have a feeling, I have a way to consider, to quantify, to focus on only some of the context rather than on other words in the context. So this is the basic of the attention mechanism. So to move the word from the embedding space to the query space, then what I do is that I pass the sequence of input vectors through a weight layer. And then I get a sequence of queries. I do the same for the keys. I pass the sequence of input vectors through a weight layer, another weight layer, not the same as for the queries, so that I obtain a sequence of key vectors. So now I have the vectors for the queries and the vectors for the keys. So I'm going to have a query vector that represents jumped, and a query vector that represents, and a key vector that represents D, a key vector that represents fox, and a key vector that represents jumped, right? So now I can match them together and see which one of the keys is the most important one. To match them together, we do a dot product. So let me show you here. We are in the space, the query keys space, and you can see that we have the key vector is relatively small because it's a relatively common word, and then you have the key vector fox and the key vector jumped, that they are both important, so both relatively big, and they are both quite aligned with the query vector jumped. So if I do the dot product between the query vector jumped and the key vector jumped, that's going to give me quite a high value because all these vectors are big and they are all aligned. If I do a dot product between the jumped query vector and the key vector fox, I'm going to have an even higher number because the key vector fox and the query vector jumped are more aligned. And those are the numbers that I obtain as attention score. So the dot product between the key vectors and the query vector, it gives me the attention score about the context with respect to the query vector that I'm examining at the moment. I wanted to tell you one more thing. So since the large language models, they predict the next word, in theory I could calculate also the attention for the words over the lazy dog. But since I'm considering now the jumped word, I'm focusing on the jump word as my query, I cannot use the words that are coming after jumped because then, those are words that are not available when I'm dealing with jumped, because jumped, once I'm in jumped, I'm supposed to predict over. So I can't use over to predict over. This is obvious. So this matrix of attention scores is going to be an upper triangular matrix. So it's going to be filled only for the half and only in the lower half of the matrix. And this is because we only have available the past words every time we are focusing on a query. Okay, so and then once you have these attention scores, of course, then you need to mask them. As I said, you need to mask the future because you don't want to involve the future in the prediction of the future. That would not be nice. And then you need to normalize it, as I said, so that you obtain some numbers that are easy to interpret, in like percentages, for example, and they have this nice property. They fall in the range 0, 1, and the neural networks deal with them easier. So you move from the attention scores, normalization, and then you end up in the attention weights in the 0, 1 range, and then all the attention weights related to that query vector, they all sum up to 1, so that I can say that it's only 10% important, but the fox is 40% important and the jumped is 50% important. So I can talk in terms of percentages, which by the humans are easier to understand.
So if you go back to the previous slide, one important point is that in reality what happens with this matrix, with these matrices, is that we have huge matrices. So in this case it's one simple 2 dimensions matrix, but in reality we have
of course,
multi-dimension. So but for simplicity, of course, we cannot really visualize that.
So the weight that I make my query so my input vector go through to get the query, and the weight matrix that I get I make my input vector go through to get the keys, those are all layers and other neural layers inside the neural network. So those are all trainable weights. They start randomly, so they make no sense at the beginning, but then they get trained, and then this alignment of the important words become more apparent with the number of iterations. So now the next step, we have the attention weights. So now the next step is to create the values vector. Same procedure, we have a weight matrix, we get the sequence of input vectors, go through the weight matrix, and we get a sequence of value vectors. So these value vectors, they represent somehow the word itself, right? The content of the word. So we have had the queries, they represent the word we focus on. The keys, they represent which word in which place of the context is important. And then we have the value vector, which is the word itself. So by multiplying the value vector by the attention weights, I'm going to produce new vectors that get emphasized if the attention weight is higher, and they get somehow reduced or so considered less if the attention weight is small. So I'm going to get a context vector for the fox and jumped, and this is the context vector for my query jumped. So at the end of all this story, I end up with 3 vectors, a sequence of 3 vectors to represent my jumped query. So as you can see, the context vectors are kind of an enriched version of the embedding vector. So the embedding vector is just a vector representation of x in a special space, of the input vector in a special space. On the opposite, the context vector is a more detailed representation of the word, of the input word, considering also the context. So I'm going to have 3 vectors that tell me not only the semantic meaning of the word that I'm focusing on, but also how important is the context around this word. So this is pretty much how the attention mechanism works. So the tokenization, so there are a few different, let's say, levels of tokenization. The easiest tokenization process is to take one word and make it into one token. This one has a bit of problems because you have many words in a vocabulary. So I don't know how many there are in the English language, but close to 1 million, something like that. So it's a lot of words. And if you have one token ID assigned to each word and then an embedding vector assigned to each word, then you can see that the dictionary explodes very, very quickly. So it becomes hard to handle. The opposite strategy is to assign like a token ID to only one character. So you have, I don't know, including the special signs and the punctuation, you have maybe 200, maybe 300 maximum characters in a language. And if you assign a token ID to each character, then you have a very small vocabulary because it's only 300 items. But you're going to have a very, very long representation of the input because you have, let's say, a sentence of 20 words. Each word must have at least, let's say, 10 characters. You can see that the sequence of token IDs become easily a sequence of 200 items. So it has the opposite problem. Very small vocabulary, but then the input sequence is unmanageable. So what they use a lot is the sub-word-based tokenization. So the tokenization that is used in GPT is frequency-based. So it's an old compression algorithm from the 90s, but basically you take the first character that is the first pair of characters that is the most frequent, and you put it together and you make it into a token. Then you get the most frequent pair of tokens, you put it together, you make it into a token. The most frequent pair of token again. So at the end you end up with pieces of words, or if you're lucky, even full words, like probably the would be a token. But then you get also, like this grammar ending, like in or the roots of the words, right? So it allows you, it's a compromise in between using the tokenization at the character level and using the tokenization at the word level. And that's what they use in the GPT. Yeah, and the whole, as Alessandro said, we need tokenization because we can't just give a word to the computer. It's not going to understand it. So we need to transform the words in numbers. And how do you transform the words in numbers? Exactly. So those are the strategies. Yeah. The masked attention that we use, it's called multi-head masked attention, masked multi-head attention. And that's because, and that's the beauty of the neural networks, they said they had one set of trainable weight matrices. So the one for the queries, the one for the keys, and one for the values. And then they thought, why don't we add a few more? And so you can have a few more. I think in GPT-3 you have 12. So you can add many more. Of course, it becomes computationally even more intensive, but they found that it actually helps to have many levels, many trainable matrices for each one of the 3 vectors that we want to generate. Okay, so this is my 10 minutes discussion of the attention mechanism.
It's priceless. It's priceless. And if we take it, if we go a level up in terms of abstraction, we also have an article about this in the My Data Guest on Substack. And the question that you were trying to answer with this article was, if ChatGPT was trained only with English text, how is it possible that it actually understands German or Italian? Not many people think about it, but when you start like thinking about it, it can be very challenging. Like how is it possible?
One of the things that when AI came out, especially ChatGPT came out, I noticed that a lot of people expected you to not to speak English, because then they would have, that you can translate it. You can ask for help in all these different languages. And then I checked how this data set was done. And I think it's a 90-something% is English text, and only 7%, I think, is some foreign languages, mainly coming from this Reddit data set. So it's not a lot. I mean, I know it's 500 billions, so even 7% of 500 billions is a lot of stuff, but still, I mean, to learn a full language based on that is, it's surprising. So yeah, there are a few things that could contribute to that. So one is Now let me remember what I wrote. But one is for sure this kind of encoding. Because the fact that you don't split by the word, but you split by the most frequent subword, then you have some subword that it's cross language, right? And it can work for many languages. Not only that, so what I've described is the word subword based, but they now use the byte pair encoding, so they go one level down and they do the subword based on bytes, and that's also covering all the UTF languages, so including the Asian languages as well. So this is one of the reasons. The other reason is that there is this thing that is called the merging capabilities. So basically, they don't know why, but it works well also for other tasks. So you train it so much and it's so big that somehow it develops also abilities that are like a secondary effect, like, you know, an unexpected effect, like in the medicine, a side effect of the learning. And somehow they develop, for example, the translation. Even though they were never trained for translations, they can do translations across languages. And that's one of the things that they're actually now studying. They are advising PhD students to study this topic because it's not fully understood, but somehow that's what happens. So those are probably the reasons, but definitely the encoding, the tokenization is a part of that.
Yeah. That's used to understand the meaning of other languages. And if people want to know more, they can check your beautiful article. So anyhow, speaking of LLMs, and if we still stay at this high kind of level of abstraction, do you know how many LLMs do we have around at the moment? Which is a very interesting question, because it's one of those questions that people kind of neglect up to the point they kind of, I don't know, talk to me and they start like explaining how I managed to run an LLM on my Raspberry, and how many even open source LLMs you can actually use. So can you say something about it?
Yeah, this is a hard question because they pop up like mushrooms. There are the most important ones. Of course, there is the Anthropic one, Claude, the Gemini by Google, of course, the GPT, the whole GPT generation. So that one, there is the Meta, the Llama, but there are many more. So now there are all the China-based LLM. So the DeepSeek was the famous one, but there are a few more coming out. So there are many, and they are coming more and more. Some of those are even open source, or as they say now, open weight. And so you could even download and inspect them and change them, reuse them, retrain them. Some of them are closed source, so you don't even know how they obtain them. But yeah, so there are, I don't know how many exactly, but it starts to be a populated landscape.
Yeah, I have a lot of experience with Mistral as well.
Right.
I use the models for fine-tuning purposes mostly, and as well as Olama open source models. That's also something I'm using a lot. Let me ask you something about all the things that you have discussed until now, because I think that probably this podcast and the things that we do are definitely a really nice resource, but it's just like one place where people can start. But if they want to know more, if they want to study these topics, if they want to be, I don't know, AI engineers, do you have, I don't know, any resource or interesting books?
So I studied in the past month quite a lot on this topic, and I used the Sebastian Raschka book. So How to Build an LLM from Scratch, I think is the title, the one by Manning Editors, publisher. And then I checked also the course by Visuara, is an educational company. And that was also very well done. I have to say it was very much going into details, but the course is also built on the Sebastian Raschka book. So at the end, it's always going back to that book. I definitely advise it. It's there is a lot of information, and it allows you to understand the little tiny details of how things have been implemented to work. So absolutely.
Yeah. That's a famous one. In addition to this, of course, since it was with us a few days ago, for another episode of the podcast. Also, Josh Stadmer has a really nice YouTube channel if you don't want to like kind of dive into all the technical concepts, but if you want to have like a general overview of how these algorithms work and have fun with these videos, because they're also a lot of fun. And yeah, so we did touch a lot of different topics when it comes with LLM. Also for me, I do have a lot of things to say, especially on the more like technical side, because I'm using a lot of these technologies. I have used them a lot, and when sometimes I have the feeling that I'm kind of touching a point where I see the limitations of the technology, but then something new pops up and I'm like, okay, now I need to kind of rethink my design, the design of my solution.
Yeah, that could be another lesson, for example, the fine tuning, because at the end we will not build a large language model from scratch. That's probably ambitious, but we might do the fine tuning of an existing one.
The fine tuning can be interesting, definitely.
That could be another topic, yeah.
I had a lot of success with that. One problem about the fine tuning is that if you show a content based on the fine tuning, then you need to maybe help people to kind of find the data set somewhere. And
yeah, of course.
Say, yeah, that's one of the problems. But also there are some other interesting topics like embeddings, reinforcement learning, shortcut connections. So probably we'll talk about these topics in different ways. It can be one like more like a lesson, like what we just did, or it can also be a more technical topic, maybe also based on what people want to see. We can collect ideas and questions and feedback, and based on what we get from the community, we can also decide if the next video about LLM is going to be a technical one or a more theoretical one. But yeah, what do you think? Can we talk about these topics in the next videos?
Sure. Let us know what you want to hear. We will study it. We will present it. Yeah. But the next one could be the tokenization, done a bit longer than in the 3 minutes I spent here.
Yeah,
something more serious.
And it can be also done on a technical level, because it's kind of easy to do. All right, Rosaria, thank you. This was great. I had a lot of fun, and I finally learned how LLMs work. Thanks to you. I didn't know anything about it before. Many thanks, and I'll see you in the next episode.
Thank you.